hit the record button. I do record these talks that we have, these sessions. We do upload them once it have been converted to the YouTube channel. So feel free to go up there if you miss one to view it. And also feel free to jump in any other session that I have. I got a 1 o'clock Tuesday and Thursday, and then of course this one here. And then Friday is my SEC students. I start at 11, but all of us are all in the same chapters. So if this time doesn't work out, feel free to jump in the other ones. Okay, let us begin with the mole concept. This particular chapter sometimes can be very confusing, but the mole concept is nothing more than a number. Okay, we're all familiar with the number a dozen, and when you say I need a dozen whatever, we know we're talking about 12. Okay, and the mole concept is nothing more than a number that we utilize in chemistry. It just happens to be a very big number. Okay, in this chapter, you may want to go back and review how to use your scientific notation on your calculator, because you'll be needing that when we do calculations, because we're working with humongous numbers. So if you don't remember, shoot me an email, refresh your memory, look at your little calculator manual, talk about putting in scientific notation, and or bring it in during the office time, Zoom office time. Okay, well let us begin. If my phone will cooperate. Okay, the mole, also known as Avogadro's number. Okay, as I mentioned, we all are familiar with the term dozen. The dozen is equal to 12. Well, Avogadro's number happens to be a little bit bigger. 6.02 times 10 to the 23rd. Okay, that is the 23rd units. The units could be bananas, oranges, whatever. But in chemistry, we talk about molecules. We talk about ions. Just a number. To give you an idea how big that number is, if you were to count that number, one number per second, it would take a few thousand years to actually get to the end of that number. So a very, very large number, named after the scientist Avogadro, which you see a picture of him there. Now, on the periodic table, we've talked in the past about the atomic weights, okay? And underneath the symbol is a number. Speaking about the periodic table, when you do these calculations and you have to use the atomic weight of an atom, use the one that we supply. You'll find if you search through the internet, periodic tables have different atomic weights. With respect to us in calculations, use the numbers that we give you on the periodic table. If you look at the periodic table, you'll see that the atomic weight of carbon is 12.01 grams. Now, all those atomic weights have a unit, and the unit is grams per mole, okay? That means that if I were to weigh out 12.01 grams of carbon, I would have exactly 1 mole of carbon atoms, or 6.02 times 10 to the 23rd. If you look up sodium, its atomic weight is 22.99 grams per mole. The same is true. If I weigh that amount out, that quantity of 22.99 grams, I have 6.02 times 10 to the 23rd. It's analogous to, eggs. If I had small eggs, I got a dozen small eggs versus a dozen large eggs. Obviously, the large eggs weigh more than bigger eggs. The sodium atom is a bigger atom, therefore it will weigh more. But in both cases, I have exactly 1 mole, 6.02 times 10 to the 23rd. Now, the mole concept is very important because we're going to learn that I can't go from A to B directly. I need to go through an intermediate, which is the mole. And being able to do that, I'm able to do all numerous types of calculations. We're going to go into detail about those in the next chapter. All right, so 1 mole, as I stated, is 6.02 times 10 to 23rd units or entities. And it could be anything. It could be atoms, it could be ions, it could be molecules, or it could be formula units. If you recall, when we were balancing chemical equations in the previous chapter, we could have, for example, A plus B, and after we balanced it, we ended up with a 2 coefficient from, say, in this example, 2. And I stated that I need 1A, because it's understood with no number in front of A, it's understood to be 1, for every 2 B's. Now I can say, when I have 1 mole of A, I need 2 moles of B for this reaction to do whatever it's going to do for this crude example, the heme B general example. Okay. So, molar mass. Okay, the molar mass is nothing more than the atomic weight of the atoms of the compound, whatever they may be. Now, you're going to hear me say molar mass when I talk about a compound, and you're going to hear me say atomic weight when I talk about the atom. Okay. Now, molar mass is when we're dealing with compounds. For example, H2O, old-fashioned water. Okay. Now, in this sample here, the molar mass of atomic weight of carbon is 12.01. Atomic weight of gold is 196.97. In every case, there's 1 mole. When you add up the atomic weights of all the atoms, for example, H2O, each hydrogen is 1.01 grams per mole. Okay, so the contribution of hydrogen is 2.0 grams per mole. It is 16 grams per mole. So the molar mass for water total would be 18.02 grams per mole. 18.02 grams per mole. Think about that. If I weigh out 18.02 grams of water, I have 6.02 times 10 molecules of water. Now think about all the water in the world, the tons of water that we have. Can you imagine for a second how many molecules of water there are? The numbers. All right. So for mass, in this example, we're asking you to calculate the molar mass of hydroxide. Well, this is where we start when we're putting formulas together. And I suggested we do that by the first ask ions before we put them together to make sure you're in the right portion. So if we look at the hydroxide, so that can be the okay. So barium has 0.2 and barium ion is straight in cycles. Therefore, barium ion has a +2 charge. Okay, that's supposed to be barium. Right. Let's try this again. My fingers with barium +2. Okay. Now the hydroxide. Well, refer you to the polyatomic ion table on the periodic table. The hydroxide ion is an OH with a negative, as a negative charge to that polyatomic ion. Remember, the hydroxide ion is a base, back to our acid-base chapter we did. I want to put these two together such that the charges cancel each other out. So you can see that I need 2 hydroxides for every barium ion. Okay, so that 2 becomes a subscript, then I'm going to put in parentheses around a hydroxide, because that's a polyatomic ion. If I need more than 1, I need to write it with parentheses. So it's Ba parentheses OH and parentheses subscript 2. Okay. Now that we got the formula, now we can calculate the molar mass. And we do that by counting all the atoms that we have and their atomic. So we have the atomic weight of the atomic weight of oxygen. And you remember 2 oxygen, 2 hydrogens. Okay, so we're down for the brain has 1.3. There are 2 oxygens between 16 and 12. Okay, so we multiply that by 2. And each hydrogen has an atomic weight of 1.01. Okay, and there's 2 of them. So the molar mass for barium hydroxide is 171.35 grams per mole. Okay. Again, if I weigh out 171.35 grams of barium hydroxide, I have 1 mole, or 6.02 times 10 to the 23rd molecules of barium hydroxide. So that's how we calculate the molar mass of any compound you're given. You add up all atomic weights for all the atoms involved in that formula. Okay, now, way back when we were doing conversion factors, going from metric to English and so forth, I talked about the ratio and how you can write that ratio one or two ways. And Avogadro's number is the same way. It's nothing more than a ratio, be it ratio being dollars per hour, miles per hour, grams per volume, grams per milliliter, things like that. So I can write it up in this manner, either on the left, where I got 6.02 times 10 to the 23rd atoms per mole, or molecules or units, whatever I'm doing, or write it like I'm going to write. Okay, the one I need to do calculation is the question. Okay, so if we look at the first question, they're asking how many calcium atoms are in 0.25 moles of calcium. Okay, and so using Avogadro's ratio, we can see we're looking for atoms. So we're going to use this factor up here on the left, okay, because we're looking for perspective. We set up as follows, and you can see here that follow your units, my moles cancel, leaving me with atoms in the numerator. Now this is where this comes forward. You get into your calculator, you type in 6.2, you double button this one, and then 3, and then multiply by 0.9, and you should come up with 1.1 times 10 to the 23rd mass. So that's roughly a quarter of it, because I'm starting off with a quarter mole. Okay. Second question asks, calculate the moles if I have 3.75 to 27 molecules of your gas. And it's looking for molecules. Okay, so what do you think which one I'm going to use? I'm going to use the one on the right. Okay, right there, because I'm looking for moles, and moles is going to be in the numerator over here, and I'm given molecules, and that's going to be so I'm going to use MLCRS shorthand. My apologies, my dog is barking in the background. I think he wants to go out. Okay. Now, in these examples, we're asked to grams to mole calculations, okay? And use the molar mass as grams per mole or moles per gram. Okay? So, first one says, how many grams is 1.667 moles of oxygen gas? Okay. Now, thing to remember is oxygen gas. It didn't say the oxygen atom, it said oxygen gas. And we know, hopefully, that now that oxygen is one of the 7 diatomic elements, so it's O2, all right? And so therefore its molar mass would be 2 oxygens, or 32 grams per mole. All right, second question, they're asking you want to calculate moles from 45 grams of silver. Here we're just talking about the element silver. So we just go look up the atomic weight for the periodic table of silver, which has the units of grams per mole. And in this case, we want to put moles in the numerator because that's what we're being asked to search for, to calculate moles. Third question, how many grams, that's what we're looking for, that's what our final units will be, is 0.554 moles of water. Okay, water. You got a compound here, so we need to figure out molar mass of water, which I did earlier. It was 18.02 grams per mole. And then the last one, you want to figure out how many grams of potassium I have if I have 4.75 times 10 to the 16 atoms of potassium. And so here you think about the problem because you're starting with atoms of potassium. And the only way I can get to grams is I need to convert the atoms of potassium to moles of potassium. Okay? All these calculations, we got to get to moles before we can go from left to right or right to left. And then the atomic weight of potassium, which we get from the periodic table. Okay. So that being said, let's run through what we did here. So, fine. Phones are picking up a little slow. All right. So first one. We're given 1.667 moles of oxygen, which is here. Okay, oxygen gas. We need the molar mass of oxygen gas, which is 32 grams. Let me change the color a little bit. Okay. All right. If we look at our units, we want grams. So grams is the numerator. Moles cancel. Okay. Leaving us with units of grams. Okay. So we set the problem up correctly. Now it's a matter of doing the mathematics. 32 times 1.667. Now, don't forget to keep track of your sig figs. We haven't forgotten those. Thing to remember about sig figs, the atomic weights or the molar mass would not play a factor in your sig figs. Atomic weights are an average. We recall average of whole numbers, so you have an infinite number of sig figs there, so we don't use it. And so our problem has begin with 4 sig figs. Our answer should end up with 4 sig figs. Okay. Second one, we're given that we have 45 grams of silver. We look up the atomic weight of silver, which is 107.87 grams per mole. Because the problem says we're looking for moles, we want moles in the numerator. Note that my grams cancel. Okay, that again would tell you I got the problem set up correctly. And now you take 45 and divide it by 107.87, you end up with 0.42 moles of silver. The third one, you're given the number of moles of water. Okay, you need the molar mass of water, which we did earlier, 18.02 grams per mole. We want grams in the numerator because, again, moles cancel, leaving us with grams because that's what the problem called for. We want to calculate the number of moles of 0.054 moles, the number of grams in 0.05554 moles of water. So that is 0.998 grams. Now, finally, the last one, let me erase all that because it's getting a little bit crazy. We're given 4.75 times 10 to the 16 atoms of potassium. Okay? We want to get to grams. So you know we're going to need the atomic weight at some point in time. But before we can do that, we need a factor. Long exam number 3 would be, I don't know yet. I just got the exam. I got to check with the department because we coordinate times. So as soon as I know for sure, I will shoot it out to everybody. Okay? Okay. So we have Avogadro's number, the ratio sitting there, because that gets us to moles of potassium. And then finally, we add the factor, the atomic weight of potassium, okay? And that gives us 2 grams of potassium. And if you check your units, you'll see that everything cancels out, resulting in unit-wise grams of potassium. Now take note of how small that number is. You start off with a humongous number of atoms, 12.75 times 10 to the 16th atoms of potassium. And if we were to get that many of them, it would only weigh 3.09 times 10 to the negative 6. Negative 6, that's a small amount. But in that small amount of matter, there's a tremendous number of atoms. Okay, so let's briefly talk about, we had molar mass. There's a new concept called molar volume. Now, this is only true for gases, okay? It's only true for gases, and it's only true under certain conditions that are called STP, standard temperature and pressure. The next slide will tell you what that is, but I can tell you now. Standard temperature is 0 degrees Celsius, and standard pressure is 1 atmosphere, okay? 1 atmosphere of pressure. Under those conditions and under those conditions only, we have a relationship that we can utilize, another ratio. If we look at these gases here, you got all these gases in here, okay? And if we have 1 mole of each, okay, we have all the same number of molecules. And obviously, because they're different atoms, they're all going to have different weights, mass, molar mass, okay, because they're different size, okay? But what they also all have in common is this relationship, the final column, that only at standard temperature and pressure, these gases, for 1 mole gas will occupy a volume of 22.4 liters. Another ratio here that we can use. Okay. That way we can relate volume to moles at STP. Only, and again, only at STP. Okay. And only for gases. Okay. That a mole of gas will occupy 22.4 liters. Now, 22.4 liters is a measure, and it's not a constant, an exact number. So if you have to use this factor, it will play a factor in sig figs. Okay? Molecular weights, molar mass, atomic weights do not. But this one is not exact. It could play a factor depending on how you set the problem. So that being the case, notice that we can set that ratio up 1 or 2 ways, like any ratio, with liters in the numerator or moles in the numerator. Which one we use depends on the question and what we're looking for. So the first question is asking you, what is the volume? That is what you're searching for unit-wise. And we're given 1.25 moles of argon gas. And what's important, it says STP. Therefore, we can use that relationship of 22.4 liters per mole. And we can set that problem up as follows. Okay, so again, our moles cancel, leaving us volume, liters. So at STP conditions, 1.25 moles of argon gas will occupy a volume of 28.0 liters. Okay. Second question. How many moles looking for moles now, would you have if you had 30.4 liters of oxygen gas? And again, the crucial part is STP. It may not tell you STP sometimes. It may say 0 degrees in 1 atmosphere. So you should be able to recognize that when they give you 0 degrees and 1 atmosphere, that you are in STP conditions, and therefore you can use that relation. Okay? All right. Set up the problem, 30.4 liters. Okay? Notice that liters cancel out. It means you got the column set up. And so 30 point, oh, balance. Okay. So notice that we have 30.4 liters of oxygen at STP conditions. That equates to 1.36 moles of oxygen. Then finally, the last one, a little bit different. We're going to need a couple factors, okay? Because the question says, what is the mass? So you see that means I'm going to need the molar mass or the atomic weight of something. What is the mass of 4.5 liters of chlorine gas? Okay, chlorine gas is one of the diatomic elements, so it's Cl2. So its molar mass will be 35.45 times 2, because there's 2 of them. Okay, and so set the problem up, and we need 2 factors. We're at STP, and then what that does, it allows us to go from liters of chlorine gas to moles of chlorine gas. Once we know that, to get to grams, we use the molar mass of chlorine, 70.90, which then gives us what we're looking for, is the mass of chlorine. So 4.5 liters of chlorine gas at STP will have a weight of 14.2 grams. Okay. All right. This flow chart really summarizes these calculations for you. Okay. The key part is moles. I cannot go directly from grams to atoms. That's no. Okay, I can't do that. Or I cannot go directly here from grams to volume, or I cannot go from atoms or units, or okay, can't go directly. I have to go through moles. Okay, I have to go through moles. And so if I have grams with the molar mass, it gives moles. And if I need to go to the number of atoms, I have Avogadro's relationship. My cell phone is a little slow. Avogadro's relationship to give me 2 atoms. And if I need to go to volume over here, if I'm dealing with a gas and at STP, then I have the relationship of 22.4 liters per mole. Okay? That, saying all that, I can go from grams all the way here, or grams over there, or from over here down to volume. Okay? And by any direction there, we can go through, forward, backward, up, down, left, right. But nothing can happen unless you go through moles. You got to convert everything to moles. Okay. All right. So, for example, let's catch up here. The question says, how many grams does 17.35 liters of neon gas mass at STP? Okay, well, let's pick up the main points here. Okay, asking you, how many grams? So that's the ultimate. Oh, my phone is really slow. Okay, asking how many grams does 17.35 liters mass at STP? And I write down unit-wise what I am looking for, so I keep track of where I'm going. I went ahead and gave you the answer there. All right. So I set up my factors. Since I have 17.35 liters of neon gas and I'm at STP, I need that first relationship right there. Okay, because that gives me moles of neon gas at STP. And once I'm at moles of STP, now with the atomic weight of argon gas, notice I'm marking off the units. My moles cancel, leaving me my grams. So if I set this up properly and just follow my units, and the units cancel out like they should, then it's just now a matter of means of just doing the mathematics, and you're good to go. So 17.35 divided by 22.4 times 20.18, you should end up with 15.6 grams of neon. Okay, so 17.35 liters of neon gas will weigh 15.6 grams of neon. The important part about these type of calculations, and that's why when we were doing the conversion chapter, okay, I emphasize set your problems up in this manner and follow your units. That's because here we are. By setting up the problems and setting up the units, you can follow through the equations, the calculations, and you will know that you got to set it up properly. Okay. Second part, it asks you how many atoms does 17.35 liters constitute? How many atoms are we dealing with? Okay, so again, this is what I'm given. I'm looking for atoms, and I gave you the answer there. But how do we set that up? We have two factors again. The first factor, again, gets us into moles, okay? But since we're looking for atoms, then I bring in Avogadro's relationship. 6.02 times 10 to the 23rd atoms per mole. That's the constant, always. So that, again, following the units, you'll see that my units all cancel out, leaving me with atoms in the numerator. Now use your scientific notation calculator, plug those numbers in, and you should end up with 4.66 times 10 to the 23rd atoms. Note the sig figs, okay? Now, I mentioned earlier that the 22.4 is a measurement and therefore is not an exact number. So therefore could play a role in your sig figs. We start out with 4 sig figs here, but we end up with 3 here, and that's because the 22.4 is 3 sig figs. Okay? The second problem had 4 sig figs, but we ended up with 3 sig figs, again, because the 22.4 has 3 sig figs, and that's the least number of sig figs, and your answer should contain no more sig figs than your least accurate measurement. All right, we lost a few, but man, we're still going with 12. 2 of those are me. Okay, so finally, density. Not finally, got a couple more things, and we're pretty much done with this chapter. Density is simply mass over volume. You may have done this experiment early in the lab, okay? But simply it's mass over volume. Any matter has density. If you measure its mass, you measure its volume, do the math, you end up with the density. But we can also calculate density using molar mass and molar volume. Again, only if we are in STP conditions, okay? Because the molar volume is 22.4 liters per mole. The molar mass is simply measuring the all the atoms involved with that particular molecule. Here, we're asked to calculate the density of ammonia gas. Here's the formula for ammonia, NH3. We got to calculate the molar mass for that. 1 nitrogen, 3 oxygens. Okay. We know the molar volume. We can set that up. Oh, come on. There we go. We can set that up. 17.04. That is the molar mass. That's 1 nitrogen, 3 hydrogens. That's 17.04 total. And the molar mass is 22.4 liters per mole. And if you look at the units, they all cancel out. The moles cancel out, leaving you with grams per liter, which is the density. So at STP, ammonia has a density of 0.761 grams per liter, okay? And that was calculated without having to do any actual measurements. We just bring the temperature down to STP, 0 degrees and 1 atmosphere, and we can do that. Okay. Now, the percent composition. This aspect is pretty straightforward. I just mentioned the molar mass. To calculate the molar mass of any molecule, we add up all the atoms and so forth. Well, we can take it one step further. Okay, let's take water. We did water earlier. Water had 2 hydrogens, 1 oxygen. Each hydrogen, the total molar mass for water was 18.02 grams. Okay, which I circled here. There's 2 hydrogens, and each hydrogen brought a total of 2.02 grams. And there's 1 oxygen, and that weighed 16.00 grams. And so if we now take what each atom brings to the molecule divided by the whole molar mass times 100, we end up with the percent composition of that molecule. So water consists of 11.2% hydrogen and 88.79% oxygen. And that is true regardless of where you get the water. You get the water here in Phoenix area, or you get the water in Egypt. So that is a constant. Okay, so these numbers should add up to 100%. And with that information, we can figure out the percent composition of any molecule as long as you're given the formula. Okay, and we use this in the real world. As I was making compounds back when I was making compounds, we would send them out for percent composition, carbon, nitrogen, oxygen, sulfur, whatever. We take those percentages and we work it back, and we can come up with a general formula for the compound we're working with. Okay, for example, let's take this one here. Find the percent composition of TNT. You may be familiar with this. This is dynamite, trinitrotoluene. Okay, the formula is given to you there. Okay, It's got 7 carbons. It's got 5 hydrogens. There are 2 nitrite groups, NO2 groups, 3 of them. That means there are 3 nitrogens and 3 oxygens, okay? So we need that bit of information. For one, we need to calculate the molar mass for that molecule. And we do that, when you do that, you come up with 227.15 grams per mole. That is the molar mass of TNT, okay? Now to calculate the percent composition, we then take each individual atom, carbon contribution, the hydrogen contribution, the nitrogen contribution, and the oxygen contribution, and divide it by the molar mass, each one times 100, and we end up with the percent composition for TNT, which consists of 37.01% of carbon, 22.2% hydrogen, 18.5% nitrogen, and 42.26 oxygen. Now, to check to make sure that your numbers are correct calculation-wise, all that should add up to be 100%. Okay, so that's a check for you. If it's not, then somewhere along the line, maybe you messed up with the percentage. That's supposed to be percentage. Okay. All right. Want to try these? Try these at home. And this is a good time. Don't forget, you can bring them into my office hours in Zoom. But I'm giving you the answers, and then really give it a shot, because you'll see a lot of these type of questions in exams and homework and quizzes. Okay. First one is, how many liters will 3.425 grams of carbon dioxide occupy at STP? There you go. That's a good hint. STP telling you, okay, I can use the relationship 22.4 liters per mole. Okay. And then they're asking you here to figure out how many liters. If you are given 3.425 grams, keep it in mind that I gotta get to moles, so I gotta convert the 3.425 grams of carbon dioxide to moles of carbon dioxide. So I need the molar mass of carbon dioxide. Right? Now, after that, given the same number of amount of carbon dioxide, how many molecules does that consist of? Okay. Again, I need to convert the 3.425 grams to moles, and now I do need Avogadro's number. I should end up, after the calculations, with 4.68 times 10 to the 23rd molecules of carbon dioxide. And then finally, the last question says, if I have 3.0 times 10 to the 15 molecules of carbon dioxide, how much does it weigh? What is the mass? Okay, so now you got molecules of carbon dioxide, convert that to moles of carbon dioxide, which then convert that to grams of carbon dioxide. You should end up with 2.2 times 10 to the negative 7 grams. So try those at home. See how that works out for you. If you have any questions, send me an email through Canvas. Again, you got to send me an email, send them through Canvas. My other EDU address is not very reliable, so send me any questions you have through email, or see me here on my office time. Other than that, the question that was brought up is the exam. I'll repeat that. Right now, I'm guessing, and I shouldn't guess. Let me find out more information. Obviously, it's gonna we have to finish. It's going to be covering chapters 10 through 12, so we include this chapter. So I would expect it maybe next week or the end of next week, early next week or late next week. Okay, but I would definitely find out today for sure, and shoot you an email. And that today, tomorrow for sure. Okay. So.
Hold on, Mr. Fred.
Yes.
Do we have exam number 3?
Yes, that's what I was saying. Exam number 3. I don't have all the information yet. It hasn't been uploaded yet. It's being edited. If it's going to be given, it's going to be over chapters 10 through 12. And it will probably be next week, early or late next week. We give you 3 days to complete it. Okay, so it's not one day, you gotta knock it out. Like exam number 2, we went Sunday, Monday, Tuesday. I would anticipate if I do it late next week, maybe Saturday, Sunday, Monday.
Okay, and you just from 10, 11, 12, right?
Yes, that's correct. 10, 11, 12. But I'll give you the exact time when it's available as soon as I know more information. Okay? Does that answer your question, Mr.?
Yeah, it does.
Okay, great. Anyone else have any other questions, comments? You go ahead and unmute yourself if you want. Let me unmute you. No questions? Okay, well, you have a good weekend. Stay safe out there. I'll have my office time Saturday. If you have any questions, feel free to drop by. It's from noon to 2 o'clock. Okay?
Thank you.
All right. Thank you, guys. You guys stay safe. Bye-bye.
Bye. Bye.